Hello, today we are looking at section 10.5, all about tangents. A tangent is a line or a line segment that intersects a circle at exactly only one point. When you take a look at the first picture on your notes, BD, the line segment, is tangent to circle A because it intersects circle A at exactly one point, which is point C. So for our example, line segment BD is tangent to circle A. It intersects circle A at point C. Point C is called the point of tangency. That's where your line and your circle intersect. If a tangent is tangent to two or more circles, it's called a common tangent. In the second picture, line L is one of the common tangents for both circles F and circle G. This picture actually has 4 common tangents. They drew in one, which is line L. Another common tangent can be drawn like this. There's a third common tangent drawn approximately like this. And one more that goes between the two circles this way. Common tangent touches two circles, each at exactly and only one point. There are a couple of theorems that go along with tangents. The first one says that if a tangent intersects a radius or diameter of a circle, it's perpendicular to that radius or diameter. So when you take a look at this third picture, here's tangent RT. It intersects the radius of circle O, which is OR. So where the radius and the tangent meet up is perpendicular, creates a right angle. So if line RT is tangent to the circle, then the radius OR is perpendicular to that tangent, line RT. The converse is also true. If I have a picture and I'm not sure whether or not a line is tangent, if it forms a right angle with a radius or a diameter, then I do in fact know that the line is tangent. So if QR and RT are perpendicular, then we know that line RT is tangent to circle O. And the last theorem for today, if two tangents come from the same exterior point outside of a circle, those two tangents must always be congruent. So this picture I think kind of looks like an asteroid or a comet. If you take a look at the circle here, there are two tangents, AB and AC. Both of them are line segments and they originate outside of the circle from the same point. Line segment AB and line segment AC therefore must be congruent according to this theorem. We can apply this last theorem to the first example. In question number 1, it says rhombus ABCD is circumscribed about circle P and has a perimeter of 32. Find the value of x. So if you remember a few chapters ago, rhombi are kind of like squares that got smushed over to the side. So all 4 sides of a rhombus have to be the same length. So first let's figure out how long each side is. So we can take our perimeter of 32 divided by 4, and each side has to be 8 units long. When I take a look at this picture, we have lots of sets of tangents that come from the same exterior point. For example, the first one I would look at is AF and AE. These two tangents both come from the exterior point A. Therefore, they have to be congruent. So if AF is 3 units, AE must also be 3 units. If you then look at the other part of this picture, which is marked, which is line segment DH, DH is also tangent to circle P. It comes from the same exterior point as tangent DE. So because DH was marked as x units long, DE must also be x units long. If we combine those two things with the fact that we figured out that each side must be 8 units, we can build an equation to say that x plus 3 must equal 8, and therefore x equals 5. When you flip over to the back of the notes, the next several examples are going to use the first theorem that we looked at. So if a tangent is drawn to a radius or a diameter, the tangent and the radius must be perpendicular. In question number 2, it says tangent MP is drawn to circle O. Find the value of x if MO is 20 units long. So here we want to focus in on triangle MPO. Triangle MPO must have a right angle where the tangent and the radius intersect. So we can use Pythagorean theorem to solve for the missing side. When we plug the sides into Pythagorean theorem, x squared plus 16 squared equals, equals 20 squared, or x squared plus 256 equals 400. That means that x squared is 144. And when we square root both sides, we see that x equals 12. In question number 3, it now says if the length of RO is 13, determine whether PR is also tangent to circle O. So if we use our answer from question number 2, PO is now 12, PR is marked as 5 units, and the directions tell us that RO is 13 units. In order to figure out if PR is tangent to the circle, we need to know whether or not it creates a right angle with PO. So we can use the 3 sides of the triangle and the converse to Pythagorean theorem to check that this is in fact a right triangle. So here we would plug in 5 squared plus 12 squared equals 13 squared, and we want to know if that's true. 5 squared is 25, 12 squared is 144, 13 squared is 169. When you combine like terms on the left side, 25 and 144 does in fact equal 169. Since triangle PRO is a right triangle, the tangent and the radius are perpendicular. So yes, PR is tangent to the circle. In question number 4, it says if ED is tangent to circle G, so as soon as I read that, I know ED and DG, the radius, are perpendicular. Then it says find the value of x. When you take a look at this triangle, there's one side, DG, that's not labeled. However, DG is a radius of the circle, as is FG. So if one radius is marked as x units long, all radii must be x units long. We know we're going to use Pythagorean theorem, so I have x squared plus 16 squared equals the entire hypotenuse, which is GE, is x plus 12 units long. So in our equation, it equals x plus 12 squared. You have to put that x plus 12 in parentheses, and I'm going to deal with that side of the equation first. Remember, you cannot simply square x and 12. When you square something, it means you multiply it by itself. So you need to write out the 2 parentheses and then FOIL Of course, if you know the special formula, you can use that as well. Either way, once you FOIL, you should get that x squared plus 24x plus 144. On the left side, I still have x squared plus 16 squared is 256. And now we can finish solving. We have an x squared on each side of the equation, so they cancel each other out. If I subtract 144 from both sides, I get that 112 equals 24x. And when we divide both sides by 24, x ends up being 4 2/3. Question number 5. In the diagram, C is the center of both circles, and the radii of the two circles are 8 and 17. So I'm going to draw one radius from the smaller circle from C to point K. That's 8 units. Then a radius for the large circle, CL, and label it 17 units. It says if JL is tangent to the smaller circle, find the length of JL. Well, I can see that if that's a tangent, it must be perpendicular to the radius that we labeled 8 units long. So I have a little right triangle. Using Pythagorean theorem again, I can solve for the length of the missing leg. So x squared plus 8 squared equals 17 squared. 8 squared is 64. 17 squared is 289. When we subtract 64 from both sides, x squared should equal 225. And the square root of 225 is 15. So the last side of this triangle is 15 units long. But be careful, they asked for the length of JL. Remember, if that line segment KC is perpendicular to JL, which is a chord in the big circle, then it bisects the chord. So if one of the halves is 15, so is the other half. So the entire segment they asked for, JL, is 30 units long. And in the very last question, it says find the perimeter of the triangle if BY, CZ, and AX are all 2.5 units, and the diameter of circle G is 5 inches. If the diameter of the circle is 5 inches, all of its radii must be 2.5 inches. Because they asked for the perimeter of the big triangle, triangle ABC, I'm going to focus in on this little triangle here, although you can pick any of the triangles of this size. The reason I'm choosing that triangle is because we can see that AB is tangent to the circle. So where it hits any of the radii, it becomes perpendicular to that radius. And now I have a right triangle where I'm missing one of the sides. So as you can see, Pythagorean theorem is very popular in this section. So again, we'll use Pythagorean theorem to solve for the missing leg. The equation for this triangle would say a squared plus 2.5 squared equals the hypotenuse here, 2.5 plus 2.5, should be 5 squared. That becomes a squared plus 6.25 equals 25, or a squared equals 18.75. When you square root both sides, and I'm just going to round to the nearest tenth, A should be 4.3. If A is 4.3, the entire side of this triangle has to be double that length. So one entire side of the triangle should be 8.6 inches. I know that all three sides of this triangle have to be the same, and that's from the fact that two tangents from the same exterior point must be congruent. FB and BE have to be the same. They come from the same exterior point. CE and CD have to be equal. AF and AD have to be equal. But it turns out that all three of the sides have to be the same. That's because every one of these little triangles, and I mentioned you could draw them anywhere, every one of these triangles ends up being congruent. Here we have our radius of 2.5 still. This hypotenuse would be 5, and if we use Pythagorean theorem on that triangle, we would end up with 4.3. So all the sides of the triangle are the same. So in order to solve for the perimeter, I know I have three sides at 8.6 inches each. And when I multiply those things, the perimeter should be about 25.8 inches. Please make sure that you complete the corresponding homework for this lesson. If you have any questions, comment on the comment section of Teams, please, or the conversations on Teams. Have a great